Alright, so today we're going to be looking at a problem involving a rotameter. So a rotameter consists of a cylindrical tube with a ball inside. And this is a device used to measure flow rate. So we have some flow that goes in, and then we'll measure the height of this ball. And based on the height, we can determine what the flow rate was. So the flow is going to push the ball up to a certain height, at which point steady state will be reached, and the ball will not have a changing velocity, or the ball won't have a velocity, it won't be moving, it will be steady there, it will not be accelerating, and therefore the net force on the ball will be 0. So first thing we're going to do is we're going to have a force balance on this ball. So what are the forces that are, working on this ball? So we've got the weight of the ball, which will be a downwards force, and then we've got the differences in pressure beneath the ball and above the ball. Those are our two forces that we need to equate, and that will be, an upward force. So let's start with the weight of the ball. So we've got two factors to consider here. We've got the actual weight of the ball, and then we've also got the buoyancy of the ball, because remember there's fluid, all around this ball. It's flowing around the ball continuously. So the ball has some sort of buoyancy within this fluid, which will counteract the weight of the ball a little bit. So we'll start with the actual weight of the ball. And we know that density, I'll write it here, so density times volume, that is equal to mass, and then we have mass times gravity, that will be equal to our weight. So we're just going to use, for the weight of the ball, we're going to use the density times, this is volume, not to be confused with velocity, which is small v, times g. So we're going to use that for the weight of our ball. So we have the density of the ball times the volume of the ball times the acceleration due to gravity. So that's the actual weight of the ball. And then we need to subtract the buoyancy from that. And the buoyancy is the weight of the fluid displaced by the ball. So in that case, we'll have the density of the fluid times that same volume, because that's the volume of the ball, again times the acceleration due to gravity. So then, for the volume of the ball, it's a sphere. We're going to say that this ball has a diameter of d naught. And we're also going to factor out like this volume times gravity, because that's in both terms. So we'll have density of the ball minus the density of the fluid, and then multiply that by, so then we're going to write out the volume of the ball, which will be pi times the diameter cubed over 6 times gravity. So that's just the volume of the sphere in terms of diameter. Right. So this is the effective weight of this ball. So the next thing we're going to consider is the pressure differences. So we're going to consider 3 separate points when we're thinking about this. So we have one here right at the very bottom of that ball. We've got 2 in between the edge of the ball and the edge of the cylinder, and then 3 right above the cylinder. So mainly we're concerned with points 1 and 3, because that's the pressure beneath the ball and pressure above the ball, and pressure beneath the ball minus pressure above the ball, that's going to be our pressure force acting on that ball, just in general. So now we could do some calculus to account for the curvature of that surface, and everything, but it's much simpler to just take into account the cross-sectional area that is perpendicular to the force acting on it. So we're going to take into account the cross-sectional area in the middle of that ball. So, well, I don't know what I'm doing. All right, so then, yeah, so we're going to have the pressure times the cross-sectional area as the pressure force. So we're going to have this equal to, so pressure 1 times the cross-sectional area of the ball, and then minus pressure 3 times the cross-sectional area of the ball. And the cross-sectional area of the ball, cross-sectional area of the ball is going to be pi d squared over 4. All right. So we're going to assume that the width between the gap between the edge of the sphere and the edge of the cylinder is so small in comparison to the width of the entire cylinder that this can be modeled as a sudden expansion. And in sudden expansion, there is no pressure recovery, and therefore the pressure at 1, or not 1, sorry, the pressure at 2 is going to be equal to the pressure at 3. And therefore we can sub in to that equation the pressure at 2. So, and we're going to factor out the area of the ball. So we're going to have the pressure of 1 minus the pressure of 2 times the area of the ball, pi d squared over 4. And this is d naught, because it's the diameter of the ball. So, next we can do some simplifying. Pi's cancel, d naughts cancel, that's 6, and that 4, that's a 2 that cancels. I think. I'll just write it out. So we're going to have that density of the ball minus the density of the fluid, and then times the diameter of the ball times the gravity over 6 times 4, so 4/6 is 2/3, and yeah, is equal to the pressure at 1 minus the pressure at 2. All right, so we've got an equation for the difference in pressure. Okay. So next thing we can think about is the Bernoulli's equation, because that is relevant to this situation here, because we've got, a fluid. All right, so we're going to look at Bernoulli's equation. So in the Bernoulli's equation, we've got the pressure at 2 minus the pressure at 1 over the density is equal, no, not equal, sorry. All right, plus the velocity at 2 squared minus the velocity at 1 squared over, no, what am I writing? Over 2. All right. So those are both relevant to our situation, and then we've got a term relevant to like the height difference between points 1 and 3, and we're going to assume that this ball is pretty tiny compared to like the entire height of the cylinder, and therefore that height difference is negligible, and we're going to have that term set to 0, so I'm not even going to write it here. And then we're also going to assume that the frictional heating in this system is negligible and can be set to 0. So that's the Bernoulli's equation that we're going to be working with for this problem. And so essentially we're going to want to substitute that in there eventually. But we need to rearrange this a little bit first. So we're going to know that the velocity at 1, but we don't necessarily know what the velocity at 2 is. So we're going to want to combine those terms. And we can do that with the flow rate. So the flow rate at 1 and the flow rate at 2 are going to have to be equivalent because, conservation of mass. We don't have any, of this fluid accumulating anywhere or it being let out anywhere. Mass that goes in is going to have to come out, and therefore the flow rates are going to have to be the same. So we have that the flow rate at 1 is equal to the flow rate at 2, and then flow rate is velocity times area. That, and then we can solve that for V1. So we'll have, so that is our V1, and then we can substitute that into this equation up here. So we have, this part stays the same for now. So then we'll have velocity of 2 squared minus velocity at 2, area of 2, area of 1 squared, where 2 is equal to 0. Alright, so then we can factor out a velocity squared. So we'll have, this is the same, and we'll have velocity squared, 2, and then times 1 minus a2 squared over a1 squared is equal to 0. Okay, so then comparatively we're going to assume that the area at 2 is very small in comparison to the cross-sectional area of this gap is very small compared to the cross-sectional area of the entire tube. And therefore, a2 over a1 is already a very small fraction, and then when you square a small number, it gets even smaller. And so this essentially goes to 0. So then we just have that pressure at 2 minus the pressure at 1 over rho plus velocity squared at 2 over 2 is equal to 0. And then we're going to solve this for the velocity at 2. So we're going to have that the velocity at 2 is equal to, so we subtract this term over to that side, which will flip the signs on these pressures. Got P1 minus P2 over rho. Multiply that 2 across, times 2, and then square root the whole thing. So then that is our equation for velocity, and we can plug this equation into here because now we have P1 minus P2. So if we do that, we also need to know that this is the density of the fluid, not the ball, because in this equation we distinguish between the two of those, so we need to do that in this equation as well. Okay, so now we can plug that in. Got that the velocity at 2 is equal to the square root, and then we've got this squared. No, it's not squared, it's just multiplied by 2. I should write this. It'll be fine. Maybe you guys can see it, yeah. Alright, so plug this in. Got it. So actually, I'm just going to write this bigger. Alright, so the velocity at 2 is equal to the square root 2 times density of the ball minus density of the fluid times the diameter of the ball times gravity, and then that 2 times that 2 is 84. That will be over 3 times the density of the fluid. So there we have our equation for the velocity. now you might be thinking, hey, wait a minute, I thought we were, trying to figure out a relationship between this flow rate and the height. We kind of don't have either flow rate or height in this equation. So next we want to kind of deal with that. So this picture I have drawn right here is a little bit misleading because as it's drawn here, this is just a straight cylinder. But if you think about it, if it's just a straight cylinder, there's only going to be one flow rate, which is going to cause this ball to reach steady state. So that's not going to be super helpful if we're trying to measure, a bunch of different flow rates and figure out what they are, because it's only going to be able to measure one. So what actually needs to happen is that this needs to be kind of angled, like a cone, but it's not necessarily going to come to a point though. And this bottom length is going to be that same diameter as the ball, because then the ball can't go any lower than that. So it's actually going to be more like that. And so we need to find a relationship between the diameter of the ball and the height, and that's how we can incorporate height into our equation. So we're just going to use a straight, the equation for a straight line, like y equals mx plus b. So we're going to have that the diameter of the ball is, or the diameter of this tube is going to be equal to some slope. We don't know what the slope is, but so we're going to use the variable m for that, times the height, we'll use h for that, and then plus the diameter of the ball. So that is our diameter of this tube. Alright, so then for our flow rates, we're going to have, so we're going to want to plug this and that into an equation for flow rate. So our general equation for flow rate is going to be the flow rate is equal to the velocity times the area. So which velocity and area do we want? So we already determined that the flow rate at 1 and the flow rate at 2 are going to be equivalent. So theoretically, we could either use either one of these two equations, but we solved for V2 over here. So we're going to want to use this one with V2 so that we can plug it in later. So velocity at 2 and area at 2. If we had solved for V1 here, which we could have done, we could have rearranged and still solved for V2, plugged it in, and just solved this for V1, then we would use the flow rate 1 equation. So then that area is going to be, so I'm not going to plug in V2 right now because I don't really want to rewrite that all a whole bunch of times. So we're going to stick it with this regular V2 for now, and I'll plug that in later. So the area at 2, so that's what we're looking at. And that area at 2 is going to be the area of the tube minus the area of the ball. And these are like the cross-sectional areas, so they're circular. So then we're going to have, so the area of the tube is going to be, so we're going to use this, that's the area of the ball, but area of the tube is going to be pi times d squared over 4, and the area of the ball is going to be pi times d naught squared over 4. So we can pull pi over 4 out of this equation. We got v squared times pi over 4, or not v squared, this is the velocity at 2, times d minus d naught squared, like that. And then we can plug this equation in for d into there. And it's going to need squared, so I'm going to do the squaring over here where I have more room. So I'm going to have mh plus So then, you know, m squared h squared plus 2 h d0 or d naught plus d naught squared. Yeah. So then we can plug that into there. And we've got that the flow rate is going to be velocity at 2 times pi over 4 times m squared times height squared plus 2 mh d naught plus d naught squared minus d naught squared. Okay. And so then obviously those cancel out. And here's where we're going to make our other approximation, that this slope is going to be very slight. It's not going to be a big wide slope. It's going to be very slight. And so that slope's going to be a small number. And again, when you square a small number, it gets even smaller. So this term will also go to 0. All right. So then we can go ahead and plug this in as well. We've got that Q is equal to square root of 4 density of the ball minus the density of the fluid times d naught times g over 3 times the density of the fluid. And we have that times. Okay, so then we've got what, pi h d naught over, and then 2 over 4, that's just 2. Like that. So now we have an equation of flow rate as it relates to the height of the ball. And you'll find that we know all of the other values in here. We can find the density of this ball. We'll know the density of the fluid that's going in. We'll know the diameter of the ball. Obviously, acceleration due to gravity is a constant. The slope of the tube, that can be measured. And then, so the height's what's changing as it relates to the flow rate. So here we have